Welcome to Dunwoody Mechanical Engineering. We've got a problem work through here on 785. So we're going to work through this in just a second, and then we're going to hopefully shore up some of the things we learned about external convection over spheres and cylinders possibly. So looking at this problem, we have a combustion chamber. We're trying to measure this gas temperature T infinity with a thermocouple. We happen to know what it is, but we want to see when we can get this thermocouple up to the temperature. And then secondly, we want to find if we have radiation between this thermocouple and the combustor wall, how much that affects the actual temperature reading. So as we look ahead to that steady state case, we're going to have Q by convection to the thermocouple, and then from the thermocouple we're going to exchange the thermal radiation with the wall, and so we'll have to balance those two and find an energy balance. It'll be a little bit of an iterative guess and check process to do that. So what do we know here? We know the velocity and temp of the exhaust gases. We also know the diameter and of the thermocouple, and then for part B, we know the emissivity of the thermocouple and T combustor for the wall here, this wall temperature. So we know that when we get to that point is let's see, that's 400 Kelvin. This, we're told, is 1000 Kelvin. Our velocity in the initial condition here, we're going to start with 5 meters per second. If we did part C, we'd vary that and see how much that impacts things. And we know this thermocouple diameter is 1 millimeter. So small bead thermocouple inside that exhaust stream. What are we looking for? We're looking for the time to, this is part A, the time to achieve 98% of final temp. I don't know if that makes sense. Maybe not the best way to phrase that. For the temperature difference between these two to reach 98% of, or maybe 2% of what the initial temperature difference was. That's part A. Part B, TC temp with radiation exchange. And then we're going to skip part C, where we would vary this velocity of the exhaust gases. So that would maybe make some sense to do in a computer tool or an Excel sheet, something of that sort. Our schematic, we've got the image from the textbook, so we're good to go with that. So we're going to jump ahead to properties. We're going to get to assumptions. So our first assumption, we're going to assume that we have lump capacitance is valid for part A. We'll verify after we make that assumption. Step 2, or part 2 of our assumptions, we're going to assume constant properties, that our exhaust composition isn't changing, or whatever else is happening is not impacting our properties of our materials. We're going to say no conduction through the leads. So we don't have any conduction flowing through these guys out through the wall. So that's going to be 0 for both of those. And then we're going to assume that the radiation occurs in a large space. Essentially that gets us Tc equals T surroundings for our emissivity calculations. Alright, and that's just for part B. Alright, so we've got those assumptions. We're going to get into the analysis here. So for part A, sorry, we need properties. Whoop! Jumping ahead again. Wow, I'm just one step ahead of myself this morning. So looking ahead, we have the TC properties are given. So we had a density. That guy was 8920 kilograms per meter cubed. Our volume's going to be pretty small, so our mass would be pretty small. We have C of 385 joules per kilogram Kelvin. And our emissivity is going to be 0.5. That's for part B. We also had the exhaust gas was also given, so we didn't have to look that up at all. And what we needed there was K 0.05 watt per meter Kelvin, and nu 50 times 10 to the negative 6 meters squared per second. And finally the Prandtl number, 0.69. So this appears to be something similar to air. It may be a little variation of that. Maybe there's a little more carbon dioxide or water vapor or something in there that's shifting these properties a little bit. But generally these are kind of air type values, so not unexpected for a gas. All right, so we've got our properties that was given to us in the book. So for part A analysis, now I'm ready there. Time to 98%. So what do we have? We're going to assume lump capacitance. If we do that, we go back to equation 5.5. And that equation, what does that tell us? We had the time to reach some temperature is rho V, where that's volume, times C, so that's some thermal capacity, over H bar AS, times the natural log of these temperature differences, Ti minus T infinity, so our initial temperature difference, over T minus T infinity. So for our given sphere here, our volume over our area, it's going to simplify down a little bit. Our initial temperature to our final temperature, or our T infinity temperature, we're going to make that 100. This is going to be 2% when we get up to that value, right? So we're going to get the ln of 50 there. So when we simplify this down, we get rho C, our volume over area turns into a density over our diameter, over 6 for a sphere H bar times the natural log of 50. So we had 100 over 2, gets us 50. When we look at that, what do we need here? We know rho, we know C, we know D, we know 6. I hope we all know 6. H bar, that's the piece we don't know. And we know the natural log of 50. So how do we find H bar? We need some correlation. What do we need for a correlation? It needs to be for a sphere. It needs to be average Nusselt. And we need to decide whether it needs to be for a laminar or turbulent. That's the question. So the way we determine that is we need a Reynolds number. Reynolds for a diameter is just V, the velocity now, not volume, D over nu. So we get 5 times 0.001 over 50 times 10 to the negative 6. And that gets us 100. So we're laminar. So our correlation, when we look through this, we need Whittaker is the correlation. And we'll get rid of that mu over mu s to the, I don't remember the power, but something of that sort. So with that, we get Nusselt for a sphere. Average is, again, that's h bar d over k. We get 2 plus 0.4 Reynolds number to the 1/2 plus 0.06 Reynolds number to the 2/3 times the Prandtl number to the 0.4. So in this case we get 2 plus 0.4, 100, 1/2, plus 0.06 times 100 to the 2/3 times 0.669, right? Yes, 69 to 0.4. So our Nusselt number works out to be, just punching it into my calculator here, I got, for my Nusselt number is 6.5626. And that is going to be h bar d over k. So h bar Nusselt times k over d, 6.5626. K was 0.5 or 0.001. And so I get h bar is 328.1 watts per meter squared Kelvin. All right, so all of that, what do we do with that now? We go back, where do we need that? We needed that back up here in our time from the lumped capacitance. So we're going to plug that in. So what do we have? We have rho, which is 8920, I believe, times C, which is 385. Yes. And then we multiply by D, which is 0.001, excuse me. And then we divide by H and 6, right? So we divide by 6 times 328.1. And we multiply that by the natural log of 50. So plugging that in, what do we get there? 8920 times 385 times 0.001 times, I get 6.824 seconds to 3 significant figures, t 6.82 seconds. So it only takes us a little less than 7 seconds to go from maybe 25C up to, what would that difference be? Whatever that is, 980 or so Kelvin, or 700, yeah, about 700 C. So we heat up pretty quickly. Not a big surprise there. It's a really small mass. So that's part A. Now for part B, what do we have going on? So we've got this convection to the surface, conduction, radiation away from the surface. We're neglecting this conduction through the leads. So part B, in energy balance, So do we have radiation? Q convection. We get H bar, AS, T infinity minus T equals epsilon AS sigma T to the fourth minus T combustor wall to the fourth. So we see that our areas are going to cancel out. Epsilon we have is 0.5, sigma is a known quantity, the Stefan-Boltzmann constant. We found H bar up here in the other part of the problem, so we're going to use 328.1. We know Tc, we know T infinity. So if we try to rearrange this a little bit, T infinity minus T equals epsilon sigma over H bar times T to the fourth minus Tc to the fourth. Again, remember these need to be in Kelvin. And this side it doesn't really matter because the difference, this is a power difference. So we'll make some guesses now. We're going to guess 900K as a first guess. We'll see where that comes out. So I get 100 on the right side, right? Equals 0.5 times 5.67 times 10 to the negative 8 over 328.1. And I could, this is going to be the same thing throughout, so maybe I'll do that here. Times 900 to the fourth minus 400 to the fourth. We'll see if we get that same difference, right? So let's see if that works out to be 100. So 0.5 times 5.67 divided by 328.1. This whole thing becomes this really tiny number, 8.64065 times 10 to the negative 11th. 900 to the fourth minus 400 to the fourth. That's 6.305 times 10 to the 11th. So we get 100 equals 54.47. Not close enough. So we're probably too cold, right? This side we had a smaller difference than that side. So it's gonna guess something else. Let's guess, we'll guess 940 Kelvin this time. So on the left side we get 60. On the other side we keep that 8.64065 times 10 to the negative 11th. If I'm guessing 940 to the fourth minus 400 to the fourth, that's times 7.55148 times 10 to the 11th. So we get 60 equals 65.2. So we maybe guessed a little too high. So I'm going to guess another one. Maybe I'm going to guess 935. And what we'll find is T is approximately 936 Kelvin after we make a couple more guesses. So there's not a direct way to solve these equations here, because we have this power to the fourth versus a power to 1. If it was just power to the fourth or just power to the 1, then we could solve it directly. In this case, it's a little more complicated than that. So what the effect of that radiation going on, we see that that is cooling down our thermocouple. That's what we expect, right? Nothing surprising there. If our emissivity was bigger, what would you see? Well, we'd see that temperature difference go even lower, right? That would pull this down. If our emissivity was lower, it would be closer to our actual measured temperature. One way that we solve this in actual practice is we put a little tube around this. So now we can heat that tube up. We're getting some radiation exchange between here and here. But it's also getting convection to it from the gases. And then we're exchanging between just that little shield and this radiation, so that pulls that up quite a bit. We get a lot closer to the actual gas temperature using this, what we call a radiation shield. So I hope that was helpful. I hope we were able to clear up any misconceptions there. Again, big picture, what are we trying to do? When we're selecting a correlation, we need to look at geometry, not geometry. We need to look at type of what we're looking for, right? An average, local, and flow regime. So we had all three of those. Found a correlation that worked well for us, this Whittaker correlation. In the book, I remember what that is, 746 maybe is what that number is. And then we use that to find that H value. And once we had that H value, we could do the other pieces of this pretty easily. Alright, thank you for watching. Sorry again for the first video not having sound. Hopefully this one is cleared up for you on that end, and we'll go from there. Thanks again.